This is 16.5, number 1. So this is the first problem in the section on divergence and curl. And our main purpose for learning divergence and curl is the applications they have towards extending our ability to evaluate line integrals, particularly line integrals over closed curves, as double integrals over areas instead. And again, it gives us the ability to move back and forth. If this problem was easy to do as a line integral over a closed curve, I would do it that way. Turns out this one is not. And the reason why is our area is once again, between 0 and 1 on x and 0 and 1 on y, so it's a square. And of course, a square is just really unpleasant to express as a vector function that traces its outside curve in a counterclockwise direction. So this one's much easier done as an area. So we want to compute both of these for these functions. And so what I need to do is first, to evaluate the first integral, I want to evaluate the curl and dot that with k hat. So to evaluate the curl here is pretty easy. I need del crossed with f, and that means I need to evaluate the partial with respect to x, partial with respect to y of xy and negative xy, and I need the determinant of that, and this will all end up in the k hat direction because any cross product in the xy plane always results in a k hat. Okay, so that's going to be the partial of x of this function, and that's negative y, minus the partial of y on this function, and that's x, and all of that's in the k hat direction. So that is the curl of this particular vector field. And now what I want to do is I want to take that curl and I want to dot it with the k hat direction. And of course, I can do that basically del cross f, which we've just found, dotted with the k hat vector, is going to be this in the k hat direction. So that makes it 0, 0, and then the third component is negative y minus x. So that's the curl vector, and then to dot that with k is just dot it with a vector that's 0, 0, 1, because k hat is a unit vector. And of course, this just results in producing that as the dot product. Remember, dot product's the scalar product, so it's negative y minus x. So this then becomes the argument of a dA vector, and the dA vector is this as the area. So I want to double integrate 0 to 1, 0 to 1 of negative y minus x dx dy. And when I finish all that, I'm going to get negative 1. So that takes care of the top one. In essence, this was equal to the integral partial d of f dot dr. So there it is. That equals negative 1. Okay, now I want to do the second one. And again, not only is the square mighty unpleasant to integrate over, but I don't want to have to calculate the normal vector for the function that I would build. Remember, the r is what gives us the normal vector. So that r is going to be piecewise defined, and then I'll need normals for each one of the pieces. Forget about it. So to do the second half, we're just going to evaluate the divergence, and that's to evaluate the del dotted with f. And of course, that just means take the partial of each component. So that's going to be partial with respect to x, partial with respect to y, dotted with the actual function x. So that's xy and negative xy. So it means take the partial with respect to x of the first component, and that's y, and then add to it, or in this case subtract the partial with respect to y of the second one. That's going to be minus x. So that is the dot product, and I just want to integrate that dA. So it's the same dA as before, 0 to 1, 0 to 1, y minus x dx dy. And when I go ahead and evaluate this, I'm going to end up with 0. So there it is, the integral f dot dr of this f over this closed loop is equal to -1, and the integral over the same closed loop of f dot n, the normal vector ds, and that'll equal 0. So there it is. These conversions into divergence and curl are just really powerful, particularly anytime where the loop would be really hard to write a vector function for.